Hello everyone, you're welcome back to Success Arena Academy. In today's video, we want to take a look at another topic in strength of material. And the topic we are going to be taking a look at today will be under stress transformation. The first thing that we'll be looking at under the stress transformation will be stress on oblique section. There are two cases to be considered when we are to determine the stress on oblique section. First of all, before starting with the case, what is an oblique section? Let's take, for instance, I have a straight bar, let me say a rectangular bar like this. That is, this rectangular bar here can be subjected to a stress which is perpendicular to its surface. Now, this stress perpendicular to its surface will be distributed equally all around the body in this. And this kind of stress here that is always perpendicular to the surface is known as normal stress. Normal stress. Now, the plane that is carrying this normal stress is known as what? Plane of normal stress. Plane of normal stress. On this plane here, the only kind of stress that this plane can carry is a normal stress. A shear stress does not take place on this plane. Simply means the maximum shear stress on this plane must be equals to 0. That means shear stress on the plane must be equals to 0. That is that for that. Now, what about if we now have something of this kind, whereby we have the plane that is sectioned at an angle. Let me say if I have something of this kind here, I said the planes are always equal. So, assuming I have a section which is normal, a section like this, which is normal to the original plane. Now, if I have a section like this that is normal to the original plane, let me start from here. I have a section like this, and that section is normal to the original plane. Now, an oblique, if I now have an oblique section like this, which is at an angle of theta with the section. Let's take this section as section E and F, and this oblique section that is here, an oblique is just a line, an oblique line is a line that makes an angle with a normal surface or with the horizontal. That is an oblique. So this is an oblique line here. Now this line F, let me say this is G. Line FG is an oblique line. Now if this oblique line is inclined at an angle of theta, now assuming we have a force that is acting on this. I said when a force is acting on this force here is going to lead to a stress. Let me say force P. The force is acting at a surface in which the area is equals to A. The stress that will be generated there should be equals to stress equals to force P all over the area. That is the stress that is there. But what about if you are to find a stress that will be on this inclined plane? Now let's take it backward, what I said. Now I said there are two cases to be considered when we are to determine the stresses on oblique section like this. The first case that we'll be considering here is a case of a member that is subjected to a direct stress in one plane. Now, if you check here, we have two planes here. This is one plane here, and this is another plane. This is a plane, this is another plane here. Now, let me try to use different color of pen so that we can understand. Now, you see, these two planes that are here are inclined at an angle of 90 degrees to each other. Altogether, now, these two planes can carry normal stresses. Now, this one can take one normal stress, and this other plane will take another normal stress. Altogether, but here we are going to take it one by one. In this video here, I will only be explaining a case of a member that is subjected only there is subject only to a direct stress in one single plane. Let's say in what? Along this plane that is perpendicular to the x-axis. So in my next video, we are going to take a look at a body that is subjected to direct stress in the two plane. That means one plane that is perpendicular to the x-axis, that is parallel to the x-axis, that is perpendicular to the x-axis, and the second plane that is parallel to the x-axis. Now, let's take the first case here. Now, we said for a case of this, I now have a body like this. Are we together? Now, if this is the normal, the body is inclined at an angle of theta with the normal. Now, what will be the stress on it? Don't forget that I said the stress that you can get on this here. Now, let's say, what is the area of this? If the area of this initial case here, the area is equals to the area, let me write it out fully. The area is equals to A. Now, the area that will be the area of this section EG, EF is A, but what about EG? Since section EG is inclined at an angle to section EF, then we can easily transfer, that means we can easily resolve the area of this section to find the area of this section that is here. Now don't forget that this material that we are considering here is of a unit thickness. And normally if we want to find the area, we can say the area is the length of the material, the length of the section that we are finding, multiplied by the thickness. That is the area. Now, the length of EF now is still EF. So the area of EF will be equal to length of EF, which is this plane that is there, multiplied by unit thickness, and the area will still remain EF. Now, what about the area of this EG? Area of EG is like this. Area of EG now will be equal to the length EG. Area of EG will be equal to length of EG, which is equal to EG multiplied by 1. Because don't forget I said this material is of unit thickness. Now, what is my EG? You will notice that my EG is at an angle of theta with the normal. Again, this is an oblique section. EG is at an angle of theta to the normal. That means I can easily resolve this. Let me try to bring out a triangle. It forms a triangle like this all together. Now, I need this side here. This one is known. Now, to get this place, which is my EG, we know that from Pythagoras theorem, trig ratio. Now, from here, if you consider this, let me say this EG here, this EG that we are talking about here is my resultant. This is the line that is adjacent to the resultant. Then we can easily find here, my EF will be equals to EG. Sorry, this is F, this is G. So my EF will be equals to EG altogether sine EG cos of theta. That is my EF, EG cos theta. Because you know that cos theta is equals to opposite. Cos theta will be equals to adjacent all over hypotenuse. And since the adjacent is equals to EF, all over hypotenuse is equals to EG. So from here we can easily make EF formula whereby EF will be equals to EG cos theta. Now, but I need EG here, then automatically my EG should be equals to what from here? My EG will be equals to EF all over cos theta. So my EG here will be EG equals to EF over cos of theta. Now, don't forget that I need the area of EG, and I said the area of EG will be equals to EG multiplied by 1. So this times 1, I'll be having EF over cos theta times 1. Now, coming back to this point here, my EF is equals to area A, then automatically EG will be equals to A over cos theta. That is the area of this section EG that we have here. Are you following on with me? Now, let's now calculate the stress that is there. Don't forget that we have a force P that is acting here. All together. Now, what will be the stress that will be acting on this surface? If I could know the area of this surface, this area EG, then the stress will be easier for me to what calculate. Now, the stress that will be here, the stress that will be on that surface should be equals to the force that is acting all over area EG. Now, and my force is P all over area EG is equals to A over cos of theta. So from there, the stress acting on it will be equals to P cos theta all over A. Since P over A is equals to stress, now I'll be having what? Stress cos theta. Now, not something, what I want you to understand in this thing that I just got here now, the stress that we got in this place here is only acting along the x-axis. Let me draw the material back. This is the oblique section. This is the oblique section that is here. The stress that we calculated here is acting along this x-axis here. But the problem is that in an oblique section, unlike a normal plane, like on a normal plane like this, on an oblique plane like this is an oblique plane. An oblique plane do carries two stresses. One stress will be perpendicular to the plane like this, will be perpendicular to the straight plane. Let me say this is point P. So it's going to carry two stress. So whereby one of the stress will be perpendicular to the plane, which is taken as Pn, and the second stress will be along the plane here. Simply means an oblique plane will carry two stresses. One will be a normal stress, and the second one will be a tangential stress. This is the tangential stress here. All together, this is tangential stress that will carry. Don't forget I'm using force here because this is a force here. So this force here will give rise to a normal. Now, this force that is perpendicular to this plane here will give us a normal stress, while this one will give us a tangential stress. Now, these are the two stresses that will be what's taking place in the material. Don't forget that we said what I only got here is along the x-axis of this bar material here. Now, if it's along the x-axis, this force here will be inclined at an angle of theta. You know, this is the normal. Don't forget that initially the plane itself is inclined at an angle of theta to the normal. Automatically, the stress on the plane should be inclined at an angle of theta to the normal. You know, I said this is a normal. Abi, along this normal here, there is a stress that is acting, which is the normal stress, and there is also a shear stress along the surface. All together. Now, this stress that we got here can be simply be resolved into a stress perpendicular to the surface and a stress along the surface. Let's try to resolve it. So, you know, the stress that we got initially was my stress should be equal to stress cos theta. Now, stress along the what normal, that is tangential to the what normal, will be given as normal cos theta times of cos theta, which will give rise to what? Normal stress cos square theta. All together, let me try to redraw the diagram so that you understand what I'm trying to say. This is the diagram here. Now, this is the section. This is the stress that is acting there. This is the perpendicular to the surface, and this is what? My theta. If there is a stress here, that is what? Sigma x. This is my normal stress. Altogether, you know, if I take this thing downward here, I can easily find what is here, and I can easily get what is along this surface here, along this surface like this. Altogether, now these are the two stress. This one is the tangential stress. This one is the normal stress. Now, the normal stress will be equals to normal times cos square theta. Now, why the tangential stress, or we call it the shear stress, because this one is acting along the surface of the material. The surface of the material, that's what the stress is acting along this surface like this. That's what we call it the tangential stress. So my tangential stress on the material will be equals to normal cos theta times sine theta, which will give rise to normal cos theta sine theta. Now I can easily do some mathematics here. The mathematics I want to do here is only that if I have normal stress tangential, I can easily say multiplying this by 2 divided by 2 cos theta sine theta, whereby mathematically, sorry, I'm dividing this stress out together, all about this thing here. Mathematically, in trigonometry, if I have 2 cos theta sine theta, it is equivalent to sine 2 theta. So from here I can easily say that what my stress all over 2 altogether, stress over 2, which is 2 cos theta sine theta, will give rise to what? Since 2 cos theta sine theta is equal to sine 2 theta, will give me what? Sine 2 theta, which is our tangential stress. So the stress on an oblique plane altogether, the stress on what? On an oblique plane is 2. We have the normal stress, which is this, and we have the what? Tangential stress, which is along the plane. Now, one thing I want you to note, I want you to understand about this stress, we can also find the maximum stress. Now, the maximum normal stress altogether on that oblique plane can only occur when my cos square theta is equals to 1. Altogether, now, maximum normal stress occur when cos square theta is equals to 1 or cos theta is equals to 1. And when do we normally get this, please? I'm trying to rub it off. Now, the maximum normal stress, you might be asked to find this. Maximum normal stress always occur when cos square theta equals to 1 or when cos theta equals 1. Now, this can only occur when theta equals 0, because we can only get cos square theta to be 1 when theta is equals to 0. Why? Because cos of theta is equals to 1. Altogether, now, when cos theta is equals to 0, we have the maximum normal stress. Why the maximum shear stress, which is your tangential stress, maximum shear stress always occur when sine 2 theta is equals to 1 or when 2 theta is equals to 90 degree. And don't forget that we can always get this 2 theta to be 90 degree altogether. Now, so simply means that means when theta is equals to 45 degree. And note something again. You know, there are some this 45 degree can also give so maximum shear stress can occur when theta is equals to 45 degree or it is equals to 135 degree. Why? Because these two angle 45 and 135 degree, they are kind of, let me say, the same angle but in opposite direction. One is less than 90, one is greater than 90, but both of them give rise to the same thing. The sine of these angles are the same and their cosines are also what? The same. Their sines are always the same, but their cosines are different. They differ only in negative altogether. So maximum shear stress occur when angle theta is equals to 45 degree or when it is 135 degree. Now, why all this? There are some questions that will be given to you in which they will say calculate the maximum normal stress. We know that what? It only occur when theta is equals to 0. That is, if I substitute in this equation, my maximum normal stress, max normal, will be equals to, you know, it is sigma cos square theta, which will be equals to what? Ordinary sigma. This is maximum normal stress. Why maximum shear stress will be equals to, maximum shear stress will be equals to this sigma over 2, you know, it's cos 2 theta. So since sine 2 theta is equals to 1, so maximum shear stress is equals to sigma all over 2. This is for this. Now, in my next video, I'm going to show you how we can calculate, the second case. We are going to take a look at the second case. You know, I said we have two cases for stresses on an oblique plane. The second case will be on the member is subjected to like direct stress in two mutually perpendicular direction altogether. So after that, I'm going to give you examples how the questions can be set and how you can take it to pass your examination altogether. Thank you for watching this episode of this series. Please don't forget to subscribe. If you are yet to subscribe to my channel, don't forget to subscribe to the channel and like the videos one by one. Are you getting me? Drop a comment for me. If there is anything that you're facing, drop a comment, or you can contact me on my WhatsApp. I'll surely attend to your messages one after the other. Thank you.